Okay, great. Hi, everyone. I'm Alex. Thanks for having me today. So today I'll be talking about this work on batching of tasks by users of pseudonymous forums, anonymity, compromise, and protection. This is joint work with my advisors, Julia Fonti and Yihar Shah, and it will appear at Sigmetrics this summer. So the setting we're operating in is online pseudonymous forums. These are websites where users take actions under pseudonyms to preserve their anonymity. So one example is an open peer review on things like openreview.net, which I'm sure many of you are super familiar with, where reviewers make publicly visible comments on papers. And it's really important that we preserve reviewer anonymity because we don't want authors of papers to know, like, hey, this person gave a really negative comment on my paper, and now I will have some form of retribution in the future. A second example is in Wikipedia article revisions. So anyone on the internet can go and edit a Wikipedia encyclopedia article, and they do so under some username that may or may not have anything to do with their real world identity. Third example is in cryptocurrency transactions. So in blockchain-based cryptocurrencies, there's a public ledger of all transactions. Therefore, people operate under some public key that represents who you should send money to and receive money from. And that public key should not be tied to their real world identity. It's just some pseudonym. And in all of these cases, a single person could have multiple pseudonyms. So in the case of open review, if you're a reviewer on multiple papers at a conference, you're associated with a different identity on each paper. On Wikipedia, you can have multiple accounts that you use for editing different things. And in cryptocurrency, it's considered a best practice to maintain multiple addresses so that people can't link together all of the transactions you've ever made to one public address and know your entire history of transactions. Now, in all of these settings, people tend to engage in a really natural behavior that we'll call batching. And batching occurs when a user completes multiple tasks at the same time. So anytime you log in and check your email and respond to all your emails at once, we'll say that you're batching your tasks. And this can actually lead to some bad privacy risk. So you think about what might happen in a peer review conference. Maybe Julia is a reviewer on a paper, and I'm also a reviewer on that paper, but I've submitted some other paper to this same conference. And so if Julia puts a comment on the paper that we're mutually reviewing at 9:02 a.m., I see that Julia made this comment. Maybe she's also reviewing my paper, so at 9:06 a.m., she batches her comments and posts on my paper. And then she says bad paper reject. And then I conclude, oh, Julia might have batched her tasks here, and really angry at Julia for giving me this bad. So an observer can link users together when they see batched events. And linking users together is usually often a first step in de-anonymizing users, because all you need is a bit of extra side information about one of these pseudonyms to figure out who all of the pseudonyms are associated with. Now, it might seem purely speculative that such a thing could happen in peer review, but we took some measurements from an actual top CS conference with thousands of papers, reviewers, and discussion comments. And we find that batching leaves a really distinct signature and timings. So if you look at the probability that a single reviewer who makes multiple comments does so within 5 minutes of each other, the probability that a pair of comments appears within 5 minutes of each other, given that they're from the same reviewer, is 30.1% at this conference. As a baseline, if you were to take a random pair of reviewers at this conference and see if they made any two comments within 5 minutes of each other throughout the entire review period, there's only a 0.66% chance that this happens. So how might you interpret this in practice if you were me and that meme? Well, let's say you had some prior over who could possibly have been the commenter, the anonymous commenter on your paper. And for simplicity, we'll say that you have a uniform prior over some number of possible reviewers. So maybe you've narrowed it down based on subject area. So after observing that a pair of comments came within 5 minutes of each other on this first paper and on your paper, your posterior puts really heavy weight on the chance that this comment came from Julia, the reviewer who batched this comment. So even if you had narrowed it down to like 10 possible reviewers, which is a pretty large number, your posterior puts like an 85% chance on the event that it's Julia. In contrast, if you were to see the comment arrive at some further time in space from that first comment, and it wasn't batched within 5 minutes, your posterior basically doesn't change at all from your prior. Yeah.
In this graph, I noticed you made I guess any other kind of information other than like in the meme you Julia was the first one.
No, we're just assuming that, yeah, I guess we're assuming that you know one other reviewer to succeed at this anonymization. So we're assuming you have some baseline comment on some other paper, and you're either seeing a comment from an anonymous reviewer that you're trying to understand, did this comment come from that reviewer or not from that reviewer? So your set of possible reviewers is like that reviewer plus a bunch of other plausible reviewers. Okay. So this is to say that there's like real privacy risk in a peer review conference. Maybe if you see batched comments in the future in a conference, you might want to put like a good chance of the fact that they came from the same person. So let's look at the application of Wikipedia. On Wikipedia, privacy is increasingly important. And so there have been a couple of high-profile cases recently where state governments have gone after Wikipedia editors who disagree with the state's opinion in Saudi Arabia and Russia and jails these people for making edits on certain controversial articles. There's also a whole host of like more mundane issues that arise with being de-anonymized on Wikipedia. People will harass you for things you wrote, or maybe you'll experience professional retribution if you post something, if you change somebody's Wikipedia page in a way they don't like. So in response to these sorts of privacy risks, Wikipedia explicitly allows that a person editing an article that's highly controversial can use some extra side account that they just use for the purpose of editing sensitive stuff. And it's really important that that's not tied to other accounts that are tied to your real world identity. Now, it turns out that batching is kind of the default behavior that people exhibit on Wikipedia. So if you look at how many minutes apart edits tend to appear on Wikipedia, about 50% of all edits are made within 5 minutes of an edit from the same user on a different article. If you expand that window out to like an hour, over 75% of all edits on Wikipedia are made within an hour of an edit from the same user in the article. Kind of makes sense when people want to edit things on Wikipedia, they'll just like log on and in some session, make a bunch of edits on a bunch of different articles. But if they do this across their pseudonyms, then again, you can link together these pseudonymous accounts and compromise their privacy. Okay. Finally, if we look at the example of cryptocurrency, we'll walk through one example here of what can go wrong. So let's say that Julia wants to send $50 to Nihar. Maybe she stores those $50 in 3 different public keys, and these should, in theory, be unlinkable. So then when she wants to send to Nihar's public key KX, she'll broadcast over a peer-to-peer network that she wants to send money from each of these keys to Nihar's output key. Then the messages will be propagated across the network. But if there's some eavesdropper who's listening on the network, they'll essentially observe that 3 transactions were sent in a batch to this output address at one time. Then they can link together these ostensibly unlinkable keys. And now they have this cluster of users who they all know are actually, of keys who they all know are tied to the same underlying person. Okay, so we've seen that batching of tasks can enable an observer to link together pseudonymous users and thereby often de-anonymize those users in problematic ways. So the goal of this work will be to design mechanisms that delay the time at which events get posted in these pseudonymous online forums in order to prevent some adversary or observer from inferring that any pair of events were batched. And we make 4 contributions towards this goal. First, we identify and formalize this new problem of de-anonymization risk. Second, we show that if you wanted to do something like standard differential privacy, we can't actually satisfy that in this setting due to a number of strong constraints on what our mechanisms are allowed to do. And that motivates a one-sided relaxation of differential privacy. Third, we propose a mechanism that we call the zero-inflated uniform mechanism that draws delay from a uniform distribution with some inflation at 0. And we prove that this is an optimal thing to do in this setting. And fourth, we run some simulations that show that this is kind of a practical thing to potentially do in these settings I've discussed. So let's start with talking about problem formulation. For concreteness, I'll discuss everything in terms of peer review for the rest of the theory portion of this talk. So we'll think about reviewers making publicly visible comments on papers on some forum like Open Review. And these comments arrive with associated timestamps, and they just arrive online. We'll say that 2 comments are batched if they arrive at the exact same time. So in this case, Elaine's comments shown in brown both arrive at time 1.2, and we'll say that's a batch pair of comments. Of course, like in reality, you cannot do things simultaneously on open review. This will just make the problem formulation much simpler, and it's easy to relax this assumption and say there's some small gap, say 5 minutes, within which batch comments will appear. The comments from Ayush and Vipul are unbatched because they just arrive alone at those time steps. Then we'll have some comment posting mechanism that sits in between when comments arrive and when they get posted. And it'll, of course, like strip the actual names of these reviewers and can decide to delay comments. And that delay can depend on whether these comments are batched or not and when they arrived. So like in this input, Elaine's comments are clearly batched. In this output, now unclear, like these two gray comments are actually batched. There's a number of natural constraints that we'll put on this sort of mechanism. We'll say that it's valid if it's delay only, so you can't post something before it arrived. We'll say that we can't introduce any fake data. So we can only release comments that actually arrived. This is a really natural assumption in peer review and Wikipedia. We don't want to like start putting fake stuff up on open review or on Wikipedia. In cryptocurrency, you could think about introducing fake transactions, but that requires people to actually like send money over the cryptocurrency network. And then they have to pay any associated fees, and people in general don't really want to pay for privacy. Probably much rather just like incur some additional latency rather than pay real money. Lastly, we can't withhold data, so you must eventually post a comment that arrives. You can't just throw it away. These all seem quite natural in this setting, but differentiates us from a lot of past work and similar problems. So maybe the most similar problem is the setting of anonymous networking. So in this setting, we think about some source and some destination that wants to send packets over a network. Usually these would be encrypted, so you don't know what the message is that's being sent, but you want to hide who the source and destination is of the packets being sent over the network. And like systems like Tor realize this sort of anonymous networking goal. And generally, the way that these systems work is each router in the network will only know who sent them a packet and who they should send a packet to. So unless all of the routers along this flow are controlled by one entity, any given router doesn't know who the source and destination was. But a long line of work going back like multiple decades now has shown that both in theory and in practice, timing analysis on these anonymous networks can totally break anonymity. For like simple sense of how that works, if an eavesdropper gets control of just the first and the last router on this flow, then what they're likely to observe is highly correlated, i.e. batch timing of packets being sent at the source and packets that they should be forwarding to the destination. And they can use that timing to correlate the initial source and the final destination for these packets. And so there's a long line of work that proposes a number of different solution concepts. This first paper by Levine et al. Says you should add some constant stream of dummy packets on the network and also randomly drop some packets as they come. And the idea there is if you're like constantly sending packets, it should hide some of these correlations. Then there's been like a lot of iterations on improving the way that you send dummy packets. More recently, there's been work that says you should send dummy packets, but actually use differential privacy to decide how many dummy packets to send. And then there's some work that says you should vary routes through the network, which will help preserve anonymity. But most of these solution concepts rely on introducing fake data or withholding data, that is adding dummy packets or dropping data. It's because this anonymous networking setting basically has the opposite costs from what we're considering in our setting. You care a lot about latency in this setting, so you really don't want to add delay if you're trying to like build an anonymous messaging service, but eating up some network bandwidth by sending fake packets is fine. In contrast, in our setting, we really don't want to introduce fake data, but adding some delay on top of all of these systems that already are not that fast is probably okay. It's not too large. Okay, so now I'll discuss how we define privacy in this setting. And a starting place is to try to define things in terms of differential privacy. Yeah.
Exactly that's what you're trying to optimize in your setting.
Sorry.
What exactly we're trying to like optimize?
Yeah, we're trying to hide that batching occurred.
Right.
But
post everything like midnight and shit.
So I guess there's two reasons. First is like gets rid of interactivity in a lot of these systems. If you want things to be like more dynamic, that might end up being quite slow. It also doesn't really protect privacy in a rigorous sense, because even if you post everything at midnight, if like only one person shows up on that given day and they batched things on that day, then you're posting both things at midnight, and that doesn't work. And then the last reason is like we want to consider protocols that can be distributed. So in settings like cryptocurrency, people probably don't all have synchronized clocks, can't necessarily agree like we're all going to always post at the same time every day. And so this will allow us to think about like everyone just adding some random delays to when they post things in a completely distributed fashion.
The thing we're trying to optimize is delivery. It's subject to.
Yeah. Okay, so we will start with differential privacy as a potential notion of what privacy means here. And informally, differential privacy would say that if you had one stream of comments with an instance of batching and one stream of comments where we got rid of that instance of batching, the outputted post times should look roughly the same on those two streams. So you couldn't tell if a given pair had been batched or not. So more formally, we would say that a comment posting mechanism M satisfies differential privacy with parameters epsilon delta if over any finite time horizon we're running the mechanism over. And for any output during that time period, the distribution of outputs on one input A and one input A prime looks roughly the same, where A and A prime are some two neighboring sets of comment derivals that differ in one batched comment. And so the definition will really depend on how we define when two sequences of comment derivals differ in one instance of batching. So let's look at some potential ways we could define this. We could say that two inputs are neighboring if you can add or remove a batched comment to get from one to the other. So in this initial instance A, Elaine made a batch pair of comments at time 1.2, and A prime is neighboring if all of the three comments in the top row arrive at the same time, but we just no longer have that batched comment. The problem here is that we're not allowed to fake data or withhold data. So on input A, we need to eventually post a comment from Elaine on paper 3 in order to not withhold data. And meanwhile, on input A prime, we can't just make up a comment that looks like that. So the distribution of outputs basically never look the same unless we fake data or withhold data. And there's no valid mechanism here. Okay, but this is like a kind of weird notion of neighboring databases, because unclear that if batching didn't occur, that a comment just shouldn't appear. It seems like it makes more sense to say, well, a comment should appear at a different time if batching didn't occur. So second attempt at defining privacy, we'll say that neighboring should mean that you move some batched comment to another time step where it's no longer batched. So let's say we took this input A, and we now will move this comment from Elaine to some later time step, time 1000. Problem that we run into here is that the unbatched comment could arrive arbitrarily far in the future. So if we look at this specific instance, because we're only allowed to delay things, this comment has to be posted at some time after 1000, which means very high probability it needs to be posted after time 1000 on input A for those two distributions. The outputs to look the same. And we can just take T like arbitrarily far in the future based on this definition. It would say we can never actually post that comment that arrives at time 1.2 on paper 3 in input A. So again, we have this result that you can't have design any valid differential private mechanism for this. Now you might say the problem that we ran into here is that a comment could arrive like arbitrarily far in the future if it weren't batched, and that doesn't really make sense. There should be some like plausible bound, we'll call that G, on how far in the future a comment could potentially arrive if it arrived unbatched instead of batched. Unfortunately, because we're only allowed to delay in this case, in other words, we could only add non-negative noise. We can't add this noise from some symmetric distribution to time. We find that any valid epsilon delta dp mechanism has to delay a comment by some factor m times this parameter g time units with probability at least 1 minus 2 delta m. So what does this mean? Well, there's no valid mechanism satisfying pure differential privacy that is delta equals 0. And in general, delta you want to take to be very small. So it'd be unacceptably long delay for any like acceptable values of delta. Okay, so one observation here is that it's only really a privacy violation when an adversary learns that two comments were batched. It's not a privacy violation if you learn that two comments were unbatched. Recall like this difference between priors and posteriors with your example that I showed before, where learning that comments were unbatched barely changes what you knew before. So differential privacy is a bit too strong because it's kind of protecting whether or not a comment was batched at all. But we only care about one of those inferences. And so there's been some previous work that tries to allow for some data to be considered non-private. For instance, if you're looking at differential privacy over databases, maybe it's we only need to care about privacy for minors, but not for people over the age of 17. And so they introduced this notion of one-sided differential privacy that allows for only some types of data to be considered private. So we'll think about how to apply that notion in this setting. So the idea is to introduce some asymmetrical notion of what it means for two inputs to a mechanism to be neighbors. And so we'll call this G neighboring. So we still have this parameter G from before that decides how far a comment could possibly move. And we'll say that we'll consider these two inputs A and AB, where B stands for batching. So AB has one more instance of batching than A. And that instance of batching can be obtained by moving some comment in A to be batched with a comment in AB, but moving it by at most G time steps. But we'll say that AB is G neighboring to A, but A is not G neighboring to AB. So this only goes in one direction. And now when we define differential privacy, we'll require that the probability of seeing an output in world AB, the probability of seeing an output in world A is bounded still by e to the epsilon. So the probability of seeing any output in AB can't be much larger than it would be if we saw it in world A. But the inverse ratio can be arbitrarily large. And what does this mean? Well, let's consider some concrete example. So say we're letting S, the set of potential outputs, be the set of events where Elaine's comment on paper 3 is posted after time equals 6. Comment is shown in red here. So suppose you had some mechanism then that releases this comment in red after time 6 with probability 0 in world AB, but with probability greater than 0 in world A. Then if you see that this event happens, you will learn that you are in world A and not world AB. But that's fine, because being in world A, all you've learned is that Elaine didn't batch her comments, and we said that's not a privacy violation. And we've also still met these constraints. In contrast, let's say that there is some event, this event happened with non-zero probability in world AB, but with 0 probability in world A. Then this first ratio is now unbounded, so it doesn't meet our privacy constraints. And this is a really bad scenario, because if this happens, then you observe that you're in world AB, because this event couldn't possibly have happened if you were in world A. And therefore, you can learn that Elaine batched her comments, which is exactly what we're trying to prevent you from learning. Okay, so now to discuss how we can actually design mechanisms with a useful trade-off between delay and privacy in this setting. Yeah.
Again, when you're trying to optimize our validity, do you mind at all if comments get reordered? I can imagine a scenario where there's like a chain of responses.
Yeah.
To keep things in order.
Yeah.
Does it actually happen?
That's a really good question. We've kind of left it open for future work. So we see in some of our experiments that this is a problem. It's also really difficult to model how to respect ordering constraints in your privacy definition, because you need some additional assumptions on how comments will arrive when you've delayed them.
Is there a mechanism also not changing the times of unbatched comments? Or you allow that?
We allow you to change the time of both batched and unbatched comments. Yeah, potentially differently. Yeah.
Can you prove that Ryan's radio strategy doesn't work? Instead of maybe instead of every day, was it every 20 minutes?
A year, but you're trying to optimize the release.
So I guess that strategy won't work to meet this definition because it's not randomized at all. You could think of that strategy as being a kind of post-processing of what we do with a little bit of extra randomness. So you could think of, for instance, saying with some probability I'll release it tonight at midnight, and with some small probability I'll release it tomorrow at midnight instead.
What's the intuition for why this is like unprivate? We disagree, like all comments ever will be released on January 1st, 2100, and you'll learn nothing about that.
Yeah, so I guess if you knew like that all comments would arrive before that time, you can always just release things at the end of a time frame. Otherwise, we run into all sorts of like worrisome edge cases potentially. So let's say you like chose some given threshold, but then you have like one user who's batching like right before that threshold, and if they hadn't batched, these comments would appear on either side of that threshold. And so if like an adversary is looking at few enough comments, like let's say an adversary has narrowed it down to either these this one reviewer made these two comments at 11:59 p.m. or this reviewer made one of these comments at 11:59 p.m. but a different reviewer made this comment, and this reviewer probably didn't make it until tomorrow. Then if you're releasing these at midnight with that set threshold, that adversary could learn that they actually came at the same time.
You can just choose that threshold over that. But maybe this would be worse than the strategy you'll show us.
Yeah, I guess.
So maybe not one day, but like what about every 30 minutes? I think that would be fine, right? And because your task is to make these two scenarios
every 30 minutes would be more problematic, because if you release things every 30 minutes, like if you release things on a shorter time frame, then it's more likely that you end up with one instance of batching that's only falling within some threshold.
Okay, well, also maybe it's just an example. I can tune in manage, like for example, like according to the frequency of the policy or something.
Yeah, so I guess like
because I feel like this strategy you can easily make these two scenarios indistinguishable, which is what you want.
I mean, we can't easily make this series indistinguishable if there's not any randomness. So I guess if you add some randomness to the thresholds, you can make things indistinguishable. But I think we can likely, like we can think of that as doing post-processing on the types of mechanisms that we've considered here, where each user has decided on some randomness that they're going to add, but maybe they all globally have decided on some thresholds and would like only release things at those thresholds. And then there's like a little bit of extra randomness as to which thresholds you release at. But yeah, I'm not entirely sure. It's an interesting question of like whether we can get a reasonable privacy guarantee for like a releasing things at set thresholds mechanism. In general, like that sort of approach though still won't work nicely in a distributed setting, I think, because you need to like have some coordination to decide what these thresholds are and exactly release things at the same time. Okay, so we'll consider mechanisms that we call random delay mechanisms to do the following. If an unbatched comment arrives, the mechanism will sample delay from some distribution U, where U stands for unbatched. And if a batched pair of comments arrives, it will sample delay from distribution B independently for each comment. And then all the comments will end up getting released at the time they arrived, plus these randomly sampled delays. And this is sort of nice in the sense that it's like really simple for people to implement locally. You just need to all like choose some distribution that you're going to use, and then you sample independently and add those to your events. And also, even if it's implemented in a centralized fashion, you can imagine some people opting in or opting out of doing this, but all of the noise is added independently to each comment. Question is, how do we choose these distributions B and U for noise that you're going to add to unbatched and batched comments? Mm-hmm.
So one way where the pushing things out in that is bad is like, for instance, sitting in the money setting, so that means that says there was one A to B and B to C transactions. And then if you batch them, then B would not receive the money, it needs to send C or something. But you said you break the ordering in this one.
Mm-hmm.
So wouldn't that happen? Like, yeah. layout?
Yeah, I think that would be a problem for many potential approaches. It's also hard to model from a privacy perspective because like we're saying there's some causal dependency between these events. So presumably if you're like withholding when you do something, then the next event in that causal chain won't even happen yet. Yeah, but it's like, I think an interesting question of how to try to design like privacy, online privacy preserving mechanisms that deal with these sorts of dependencies. Okay, so we'll show that if distribution satisfies some property, we'll call it being one-sided and distinguishable properties epsilon and g, then that's sufficient for preserving privacy given our one-sided DP definition. So what our mechanism will do is for this first comment from a lane at time equals 0, it'll delay by D1 that's drawn from distribution B on input AB. And in input A, it'll draw from distribution D1 that's distributed according to U, because it's an unbatched comment there. So we want to require that distribution B is quite similar to distribution U up to this factor e to the epsilon. And now for the second comment, it'll be delayed by a draw from B on input AB, but on input A, it's being delayed from a draw from distribution U, but let's say it arrived at time t equals G. So now its distribution follows like offset G plus U. So we require that the distribution of B is close to the distribution of U plus G. And we can vary where the second comment arrives anywhere between 0 and G. We got that like the distribution of B and U plus A should be similar for any A in range 0 to G.
What is G?
Yeah, so G is a parameter of our privacy model. It's supposed to summarize like all domain knowledge about how far in the future a comment would plausibly arrive if it were unbatched. It's kind of like that interpretation alone, it's like hard to set it as. So what we think of it as is like some large percentile of the historical inter-arrivals of when comments arrive if they're unbatched. You can think of like if an adversary had some baseline distribution, this is how frequently comments arrive if they aren't batched. And they're trying to distinguish, did this pair of comments come from that distribution of unbatched comment inter-arrival times, or did they come at the same time? Then if we chose some large percentile of that distribution, we should have a hard time distinguishing.
So do you think like each person sends like at least one comment per time G, or one comment to send for every time G?
Yeah, I guess in our definition, it means that at least one comment is sent within time G.
The interval length G
For every
one
input.
comment?
Yeah. Okay, so one example of a distribution that we could use that meets this definition is the exponential distribution. And this basically is actually just exactly taking what you would do for normal DP and making it one-sided. So like one of the basic things you do for differential privacy is you could add noise drawn from a Laplace distribution. And here we're just taking one tail of the Laplace distribution. This is an exponential distribution with rate parameter epsilon over G. And the distribution for U is set at 0. The distribution for B is just the same distribution shifted over by G to the right. Right. So now like the distribution of B and U plus G are just equivalent everywhere. And we look at any given point, the difference between the probability of B and the probability of U is actually exactly equal to e to the epsilon. So we meet these constraints. Some sense this is not very interesting because this is like if you just looked at what you would normally do for DP and said we could only make it non-negative, it's like exactly what you would do. Interestingly, we can actually also draw noise from a uniform distribution. When these aren't even distributions with like the same shape. So in this case, again, the unbatched comments will have support from 0 to some upper limit. The batched comments will have support from G to some upper limit. And so as long as the height between these two distributions is bounded by e to the epsilon, we'll be able to meet our constraint because wherever the distribution B is equal to 0, it's like by definition less than this right-hand side. And wherever it's non-zero, we go G to the left, we will end up with a ratio that's bounded by e to the epsilon. And so it turns out that adding noise from a uniform distribution is actually the optimal thing to do in this case. So we can prove that the Pareto optimal distribution in minimizing expected value to batch, expected delay of batched comments, expected delay to unbatched comments is a zero inflated uniform. And by that, I mean that the delay to batched comments will always be uniform. But the delay to unbatched comments, we will upsample zero with some probability 1 minus eta. And your choice of eta can allow you to move along this Pareto frontier. And our proof here adapts a proof idea from this paper, The Optimal Mechanism in Differential Privacy, which looks at if you just have some query of your data and you want to release that query plus some additive noise, what noise distribution should you use to guarantee differential privacy? And they show that the distribution you should use is something called the staircase distribution, which roughly looks like a Laplace distribution. You take the PDF of the Laplace distribution and like discretize it into some step sizes, and it leads to marginally better expected absolute error in large privacy regime. But roughly you can think of it, this is saying like the Laplace distribution is very close to optimal. There's like optimization you can do. So it's actually like a very different distribution to be using than what you would do in standard DP.
Can you explain, so from what you're saying, I understand that you're also postponing or possibly postponing